the title of my talk, Analysis Tricks. This morning's session is going to be a little bit like two 20-minute talks. The first one is going to be me sharing some analysis tricks with you. And the second part is going to be on, I want to share with you some sort of findings from some AX testing I've done. And hopefully what I'm going to say will follow on quite nicely from what Wes said in the opening talk of this conference. So that's going to be the second part. First part is we're going to try and do some tricks. So I'm going to start off with one, hopefully, if this mirroring is going to work. Perfect. Okay, what I wonder is, could you give me a single-digit number? 7. Beautiful. So we've got 7. Sam, could you give me another single-digit number? 7. 7. No, 7's fine. I'm not going to influence what people say at all. So we've got a 2-digit number now, 77. Hopefully randomly selected. So we're going to try something. It's just a bit of a trick, and we're going to see if it works. So let me try and fill in my little grid here. We're going to start with everyone's favourite 10s and 3s, because that's a good Wi-Fi numbers. My favourite number I'm going to put down here, which is number 4. Let's have number 1 at the top there. And then I'm going to fill in the rest a little bit quicker, and we'll see how this goes. So then we're going to go with 2, 3, 5, 9, 6. Okay, I've got some numbers written down. Hopefully everybody can read them. What we're going to try and do here is we're just going to try and add up these numbers. So I don't know if people like math, but let's just have a look at the numbers across the top row there for them. We've got 57 plus 1 is 58 plus 12 and plus 7, 77. Not bad. Let's do the next row. We've got 11 plus 8 plus 56 plus 2 is also 77. 5 plus 10 plus 3 plus 58 is 77. And across the bottom, 4 plus 58 plus 6 plus 9 is 77. Not bad for a start. Let's just work down the columns. We've got 57 plus 11 plus 5 plus 4 is also 77. 1 plus 8 plus 10 plus 58 is 77. 12 plus 56 plus 3 plus 6 is 77. And if we go 7 plus 2 plus 59 plus 9, we also get 77. Not bad. What if we take, I don't want to clap just yet. What if we take our diagonals? So if we say 57 plus 8 plus 3 plus 9, that equals 77. If we take the other diagonal, 7 plus 56 plus 10 plus 4, that also equals 77. But we can also take the corner numbers. And you might find that 57 plus 7 plus 9 plus 4 is also equal to 77. If we take just this square here, we've got 57 plus 11 plus 8 plus 1 is also 77. And we can also take this square of numbers here, and we've got 7 plus 2 plus 56 plus 12 is 77. If we take this square down here, we've got 6 plus 9 plus 3 plus 59 is also 77. Here we have another square of numbers 4 plus 5 plus 10 plus 58 is also 77. We can also take the square in the middle. Oh. Look at this. It was asking me to subscribe. Maybe later. 8 plus 56 plus 10 plus 3 is also 57. And I can also take this square of numbers here. And you might find it's also 77, and this square here is also 77. Not bad. You can clap now. So that is literally just a trick. And it just thought it'd be a good warm-up for me before I start showing you some other tricks. There's one other thing I want to quickly show you as well as I start this presentation. We'll wait for it to click on. Something some of you might know, something I shared with the community a few months back was a little PowerShell script I wrote. If you want to get hold of it, you can go to mackenziewifi.com. There's a blog post on there and a link to the GitHub. Or, follow me on Twitter at MackenzieWiFi. I'm going to blog about a new version I'm going to do quite soon. But let me tell you some of the things about its script, why I like it, and why it's actually quite a good way of solving problems on networks. All this script is doing, let me quickly show you, all it's doing is it's looking at the net SH output and just putting it into a GUI. So you can see which BSS you're connected to, you can see your data rate, you can see the SSID. It runs on Windows. Now, we were once in a hospital scenario, and I wonder if this is familiar with some people like this, is they took me to a spot on the ward and they said, here is a really bad signal place for Wi-Fi. We can never get connection here. And I look up and there's an AP above our heads. And I do a bit and a really strong signal from it, and I'm saying, why is this a bad place for Wi-Fi? Well, and they said, and the problem was they had these computer on wheels, these cows that they used to move around, the drug trolleys, and they always did the ward round in the same order. And they said, every time we get here, we lose connection, we have a really poor performance, the application is slow, we can't get the drugs. It was always in the same place. So I ran this PowerShell script on the computer on wheels, and then I literally took it through the ward, the way they go. One of the nice things about this is it'll show me every time I roam. I didn't see any roaming. So by the time we got to here, it was still associated onto the AP at the other end of the ward. So actually the issue that we were seeing wasn't that this was a bad no coverage area. The fact is the client was never roaming. And it's really easy to see if you've got some way of being able to monitor which BSS you're connected to, where, and when you're roaming. So really useful. It's because it's a script, it's really easy just to copy onto other devices, and you can run it like we run it on this computer on wheels. And I'm hoping people will find it useful. So if you want to get hold of it, as I say, go on my website, you can download it. It is a script, so you can modify it, you can change it. Some people have already modified it and added other fields to it, other information. So have fun with it. That's just a little WLAN monitor script. Okay, first thing to talk about when we're talking about analysis tricks. Now, I'm going to share with you two main tricks which I use a lot when troubleshooting. And these aren't per se wireless tricks. I've shared in the past in other talks lots of wireless tricks. These are just general protocol analysis tricks. And when we're doing protocol analysis, there's many places we can capture data. One option is to capture near the client. And if that's a wireless client, we're probably going to be doing some sort of wireless packet capture, maybe with Wireshark, OmniPeak, some sort of tool that we can do a wireless packet capture. Every time I do wireless packet captures, the very first thing I do when I'm troubleshooting as a client is I also set up a wired capture every time, because the wireless capture is only going to show me so much. First of all, if the data is encrypted and it's an application issue that the user is experiencing, I'm not going to see it. So for looking at more, and what if we check that the wireless actually seems to be working? Then where do we look next? And so other places we can do captures, you may choose to capture directly behind the access point. Maybe you can mirror the port going to the AP. Maybe you can put a tap on it, and you can look at all traffic behind the access point of interest. Sometimes you don't know which AP the client's going to be connected to, so monitoring maybe traffic going to and from the wireless and controller will give you that information if traffic is being tunneled back to the controller. Other times, you could mirror maybe a whole wireless VLAN, or sometimes, it's a problem with a particular application. So monitoring the application traffic is of interest. So there's many different places we may monitor traffic on the network. And as we do that, depending on where we capture traffic will depend on what we see. And when we're talking about network delay, which is, how many times is the Wi-Fi slow? And how many times can we explain why it's slow? So when we're talking about network delay, depending on where we capture will depend on what we see. So this is where delay occurs in a network conversation. You've got network delay from the user to the application that they're using. Then you've got the processing time of the application. The server's going to take that packet, going to process it, and send a response back. And then the response coming back is going to also experience network delay. So if we're capturing at the user, we're going to see what we call round-trip time. That is the network delay, the one-way network delay, server processing time, network delay coming back. That's the round-trip time. If we are capturing by the application server, we are just going to see server processing time. So how can do we always have to have two captures? And how can we identify, is it the network that's slow or is it the server? And can we do that from just one capture? Well, that's the first trick I really want to share with you this morning. And I want to talk about two fields. As I say, these aren't wireless fields. These are just general fields we're going to see in networking. The first one is the IPID. This is a field in the IP header, and it's used to uniquely identify IP datagrams. Every IP packet that a station sends out has a unique IP identifier, and they count up with 1. And it's not within a conversation, it's every IP packet I send out. So if I send a packet to a destination over there, that might be IP identifier 1. The next one, IPID 2, IPID 3, IPID 4. So that's IP identifier. The next important thing I want to talk about is window size. Window size is in the TCP header, TCP window size. And the TCP window size basically tells me the size of the buffer in the receiver. Okay? And what a client is saying in advertising its window size is, hey, I've got this much buffer space left to receive packets in my TCP stack. And I can keep receiving frames. And that tells us what that is. So why are those two things important? Well, first of all, this is where you're going to find them. So the IP identifier is in the IP header here. And then we need to look in the TCP header to find the window size. Now, we can use these two values to identify, is it the network or is it the server? Just these two fields tell me that information. Let's have a look at this actually in a packet trace file. I've got a packet trace file here of a conversation where they were experiencing network delays. It was slow, okay? The application, the network, we weren't really sure what, but the user was really slow. And what I've done here is I've put up here the IPID column and window size as columns in this conversation. I will zoom in a minute so you can see in a bit more detail. Now, things we're looking for. If we see the IP identifier going up by 1, we know we're seeing every single IP packet that the client and the server transmits. If we see big, so this is only filtered on one conversation, if I see big gaps in the IP identifier, I know that between the 2 packets in this conversation, the server also sent out lots of other packets to other destinations. I might not know what, but it tells me that they're busy doing other things. They're serving other clients as well as me. Okay? The window size, what we want to see is it remain the same sort of value. Because if the window size starts going low, that's the server saying, whoa, I've got no more space in my buffer, stop sending me data. If it ever hits 0, that's what it says. If it finally gets to 0, it's like, stop, don't send me more data, can't cope. So it tells you that it can give you an indication that the server's running out of resources. So there's the things we're looking at. To make this easy, what you may notice is I've already put client server in my name table. Client is red and the server is blue. So I'm going to color the text in every line by whoever is sending this data. So I'm just going to color by source. So now all the red lines are sent by the client, all the blue lines are sent by the server. I will zoom in to our window size and IP identifier. Now in this conversation, we can see a few things. If we look at the window size of the red is a client, first of all, we can see that it's quite a big window size, lots of receive buffer left, and it's more or less, it's staying around the 7,000 mark. It sometimes drops to 16,000, which is what you want the window size to go up and down a bit, but it looks reasonable at the beginning of this conversation. If we look at the buffer size in the server, it's a bit lower, but it's 8,700, and again, it seems to be going up and down a bit, but the window size seems reasonably okay at this point in the conversation. Let's have a look at the IP identifiers. Again, if we look at the client, which is red, we see the last 3 digits are 740, the next one 741, 742, 743, 744. It looks like this conversation is pretty much all the client's doing. It's not sending IP packets anywhere else. If we look at the server, it's a slightly different story. We've got 50,342, and if we look at the last 3 digits, it then jumps to 598. So it sent about 200 packets between those 2 packets to other destinations. If we look and we keep looking down, we can see them sort of increasing by a few hundred at a time. So this server is definitely busy serving other clients. Again, not necessarily a problem, providing the network is performing okay. Let's have a bit of a look then at, scroll down and look at a bit further down in this conversation. And see if we can identify what's causing the delay. I'm going to take us just to a place I know. Let's have another zoom in at this point. Now, at this point, the window sizes still look quite good, but if we look at the IP identifier, this blue one, this is really interesting at this point. The server, between these 2 packets it transmitted, and when we look at the time difference, this was about 0.4 seconds between them, and it sent out about 10,000 other packets then in that time, which is quite a lot of other IP packets for a server to be sending out, which suggests to me this is a very busy network server. As we scroll down even more, and I'm just going to zoom out so I can get to the right point in this conversation. Let's see what that carries on happening. The server seems to get more and more busy. And then what we eventually see, I can get to, again, I'm going to zoom in here. As the server gets more and more busy, we see its window size there dropping. 8,048, 5,000, 2,000. It does jump up a little bit, then it gets sent some big frames, and all of a sudden it hits 0. You don't want to see a window size hit 0. That is literally the server saying, stop sending me data. And we start seeing big network delays. So from looking at just these two fields, we can identify, or from here, although we were literally capturing by the client, we can identify that it's not the network, it's the server that's having difficulty on this network. So it's not the Wi-Fi. Oh, I'm zoomed in, that's why it's struggling. That was trick number 1. The second trick is one of the things I'm always talking about. I say this a lot when I teach CWAP courses. When you're looking at packets, one of the questions you need to be able to answer is, where's it come from? Where is it going to? Where's the packet come from and where is it going to? Now, if we look at this few packets I've put on the screen here, I'm sorry for the guys in the back. If it's small, I'll explain what's in them. The first 2 packets we see are DNS responses to a query that's gone out. So I've obviously not captured a query, but it's a small bit. And we see the same query response twice. It says it's a query response for hope.edu. The source and destination are the same. It almost seems to be the same packet twice we're seeing. Okay, so it looks like we've captured the same packet twice. Following that, once you've done a DNS query, what do you normally expect someone to do? Try and connect to that website. So they're going to establish a TCP connection with the web server. And we establish TCP connections with the three-way handshake, SYN, SYNAC, ACK. But what do we see? Well, it's a little bit small, but I'll try and point it out. This is a summary of the TCP information, and we see a SYN, we see a SYNAC coming back, and then we see a SYN again, and a SYNAC, and a SYN, and a SYNAC. It never completes a handshake. We see it repeatedly trying to connect. SYN, SYNAC, SYN, SYNAC, SYN, SYNAC. Why? What's going on? Well, let's try and answer the question, where are these packets actually coming from and where are they going to? Now, to do this, I'm going to add 2 more columns in here. We've got the source and destination IP address shown. Let's just add in the source and destination MAC address too. Now, what I like to do when answering the question is draw a picture. I will literally sometimes get my notebook and I will draw a picture of what's happening. And that can tell us so much. So that's what I want to show you today. And this is just a little trick to understand the flow of packets. So we're going to take packet number 1, and we're going to write down the source IP address and the source MAC address. And then I'm going to draw an arrow to the destination MAC address and IP address. So packet 1, there's my source and destination IP address and source and destination MAC address. That is where it's coming from and going to. I'm then going to take the next packet and do the same thing. When I see the next packet, I can see that the source address is the same address as the destination address for the let's packet, but it's a different IP address associated with it. So let me write that IP address down as well. And where's it going to? Well, it's going to 774D. So I'm going to draw a line and say, hey, there's packet number 2. Now, when I get a MAC address with multiple IP addresses associated with it, that's because it's likely to be a router. because it's packets flown through a router. So I know those IP addresses don't really belong to that MAC address, so I can get rid of them because that is some sort of router. And it would also explain why I'm seeing the same packet twice. It's going to the router, it's coming from the router in this trace file. So I'm seeing both sides of this routed conversation. It's the segment of the network I'm looking at. Okay, let's take the next packet. The next packet is the first SYN packet, and it's coming from an IP address that ends 183.21, and it's going to another MAC address that we've not seen yet. So let's draw that one. That's packet number 3. And then when we see the SYNAC come back, which is the next packet down, we then have yet another MAC address in this conversation. We don't have these many IP addresses, but we've got all these different MAC addresses. And we can see it's coming from this other MAC address that's also claiming to be 98.20. And it's going, not back, although the IP address it's going to is 21, it's going to that router we identified earlier. So that's the flow. And if we look at the next SYN, we'll see it's a repeat of the first one, and the one coming back is the same, the next one, the same, and the same again. So what is going on with this conversation? We've drawn it out, but why? What's going on? Well, the next thing I want to do is I would want to start identifying what some of those MAC addresses are. So I'm going to go and talk to the customer, say, do you know what this MAC address is? Can we identify the equipment that these devices belong to? Because there's some funny routing going on in this network, and I want to identify what the issues is. So we go and have a look up some of those MAC addresses, and we find out that that first one that we saw the DNS query response coming from was the ISP router. And it was going to the firewall, and then we saw it coming from the firewall to our client. That makes sense. The default gateway for the subnet that the client was in was also the packet we saw it sending the SYN to. So it receives packets inbound via one firewall, and it goes out via another router. Nothing unusual there. But the unusual bit is there's a MAC address that we didn't know what it was. And that was this MAC address there in the middle at the bottom, where we saw the response to the SYN coming from, and it was going to the firewall. But we never saw it coming out of the firewall, did we, back to the client? That's why the connection wasn't working. When we investigated this a bit more, we found that the ISP were replacing their routers. And for a little bit of time, they were running 2 in parallel. And this was a second ISP router, but there was no rule for it in the company firewall. So the company firewall was blocking all traffic from this firewall. And that's why the packets weren't ever being forwarded on. Now, I just wanted to show you that tip because drawing out on a bit of paper can be a very quick way of identifying where a packet's coming from, where it's going to. When you just look at the packets in an analyzer, it's really hard to see that. So that's my second little tip for you, is draw it out on a bit of paper. Okay, now for the 802.11ax bit. I was going to call this the boring 802.11ax bit. Why boring? Because I think so many people, when they talk about AX, don't they? They tell you about how it's going to change your life. It's going to change networking. It's going to make it's sexy, isn't it? And I'm not going to do that. So, but hopefully you're still going to find it interesting. Now, 802.11ax, it's high efficiency. That is what we're being promised. I've put a question mark on efficiency, because that's what I want to talk to you about this morning, is how efficient really is 802.11ax. We're promised efficiency, but is it really? Well, before we go into that, into answering that question, I want to try and explain a little bit about how it works. A lot of people have been asking me, when are we going to have AX in CWAP? Well, it's going to be in the next version. So let me give you a sneak preview to some of the things you might learn And then we'll see if people still are desperate for it to be included. 802.11ax introduces 4 new PPDU formats, 4 new physical layer formats. Here they are. The very top one in this list is what we call a single user physical layer protocol data unit. So it's a high efficiency single user PPDU. This is the physical layer format it's going to use when we're just talking to one user. So we're not using OFDMA, we're just transmitting to one device using a Hurl channel. That's the physical layer format we're going to use. The next one down there is what we call the high efficiency multi-user PPDU. This PPDU is used for downlink OFDMA. This is when the AP is going to be transmitting to multiple devices by subdividing the channel into different RUs and talking to more than one user at the same time. This is the format it's going to use. That's the second one down. Now, the third one is something which it calls a high-efficiency extended rate single-user PPDU. I'm not going to talk too much about that one because it's used for, as I say, extended range. The idea is for things like outdoor bridge links. Today, I've never actually seen it being used in the wild. I'm not saying it's not going to be, but it's not one that I think we're going to see as much of in things like captures and datas. And then the fourth one is called the high efficiency, HE, trigger-based physical layer protocol data unit. So it's the HETB PPDU. And that one's used for uplink OFDMA. Okay? So that's used by clients for sending data in their resource unit towards the AP. That's the format they're going to use. So there are our 4 formats. Let's have a look at what we can see in them, okay? And why are they interesting? So these first 3 fields are what we call the legacy PHY header. So there's a legacy short training field, a legacy long training field, and a legacy signal. What do we mean by legacy? Basically, a legacy OFDM PHY header. That's an A and a G PHY header. It's not an AX one, it's not an AC one, it's an AG PHY header. They were the PHY headers. And that's there for backwards compatibility, because when we send a high efficiency data frame, we want to make sure that A, B, G, and AC devices can all at least read the PHY header so they know a frame's coming, even if they can't read the rest of the PPDU. They can see the PHY header, they know a frame's come in, and they know to therefore reserve, be quiet for that frame transmission. So that's why that bit exists. The next little bit is quite interesting. This is what we call the RL sig, or the repeated legacy signal field. It is just an exact copy of the legacy signal field we've already sent. Repeated again. Efficient, eh? We send it again, and the reason we send it again is to indicate that the thing that's coming next is HE. So that the receiving station knows that the next thing that's going to happen is going to be a HE header, not an 802.11n header, not another type, a AC header. It's going to be an AX header. It's going to be a HE header. So we repeat the same legacy signal field. Seems a bit odd, but that was the way they decided to do it. Following the repeated signal field is something called a HE sig A field. And this contains all the information necessary to interpret the data part of this frame. So it's going to talk about things like what data rate is it going to be sent at, what spatial streams is it going to be, is it sent with multi-user or is it single user? It's all the information about the data that we're transmitting and how to receive it. Nothing new with a SIG-A. We had SIG-A fields with AC headers. Then in we've got something called a HE SIG-B. Now, the only one of these formats that has a SIG-B is the downlink OFDMA one. Because in here is where we're going to say which users, by association ID, does this frame contain data for? So who is it for? Because it's for multiple users. So it contains the association ID, and it contains information on which resource unit that those users have. So it tells the users that this frame's that's in for, hey, this is for you, this is which bit of the channel is for you, so they can receive their data. So that's where we get a SIG-B from. Following that, we have these what are called long training fields. And these long training fields, literally, I'm not going to go into too much detail from them, but we send one for sort of every spatial stream, and they're there for the receiver to estimate a channel, the MIMO channel. And we use them when we're doing things like sounding the channel, when we do things like transmit beamforming, multi-user MIMO, and things like that. So we use them for being able to understand the multi-user, the MIMO channel between the receiver and the transmitter. So they're literally, that's what those parts are used for. Now, so they are the 4 frame formats that we have to learn. And I say there's 4 frame formats, but there's also 2 modified versions of these frame formats used for something called null data packets. Null data packets are when we send just a PHY header but no MAC layer data. And we use them for channel sounding, and we use them for communicating data about a channel when we don't want to do sounding. That's what the second one is. A little bit more complicated. We're not going to go into too much detail on them, but these are 2 variations on the header when we just want to send header information, and we call them null data packets. And we have 2 versions of them. Then we also have a MAC frame format called a trigger frame. And this is an important frame, because a trigger frame is a frame that the AP uses to trigger things like OFDMA. When we want to say, hey, these stations, you can all send data now, or I'm about to send data to you. It's used in lots of different ways. And this is what a trigger frame looks like. Again, there's a lot of information on this slide. I'm not going to go into it. I'm not teaching a new CWAP class. How many people are looking forward to a CWAP class now? Oh yes, this is sort of stuff you're going to have to learn. But very simply in here, there's something called a common info. And the common info has information about the sort of channel and also the trigger frame itself. Now, there's lots and lots of different trigger types. We've got a basic trigger type, a beamforming, Perl report, multi-user block acknowledgements, multi-user RTS. There's a whole host of different trigger formats. Again, I'm not going to explain them all. When we will be going into more detail later on if we talk about the updated CWAP class. This is the sort of stuff we're going to be learning. And then there's also some user info. And the user info is saying, hey, this is a trigger frame for which users, which association IDs. It's also going to say what resource unit you can have, which bit of the channel you can use. So all of this information is all new stuff defined in AX. So one of the reasons I wanted to point all this out is because when we start to look at AX packet captures, which I'm going to show you next, this is the sort of stuff we see in them. Now, this is only a subsection of an AX packet capture, but you will notice some of those information in here. If we look at this PPDU format, this shows me some of the different formats that we saw initially. So I can see a HE single user frame. I can see HE trigger-based frames, HE multi-user MIMO format. We can see the different PPDU formats. We can also see different bandwidth allocation in terms of use. There's some here which are, there's 106 tones, frame being sent with 106 tones, here's one with 242 tones. So we can see different tone information. You'll also notice some new different frame types. Here's these trigger frame that we've just talked about. Sometimes the response to a trigger frame is an action frame, which is called NOAC. You'll also notice this is something called a very high throughput, or HE, NDP announcement. Now that was a control frame which was introduced with 802.11ac, but HE uses it too. And it says, hey, the next frame is going to be one of these null data packets. File header only. And that's actually what we see next. There's a sort of, it says type, subtype, and it's blank because we've just got header information in the next frame. There's no actual MAC frame included in it. So when we're looking at AX trace files, they get quite complicated quite quickly. There's also a lot of overhead. This is doing OFDMA, and there's lots and lots of frames needed to achieve it. So again, my question comes, and what I'm thinking is, how efficient actually is OFDMA? If we've got to send all these frames, and we've got to do sound in, and we've got to do trigger, is it really efficient? So that's my question from a protocol point of view. What about a spectrum point of view? Because one of the big claims of OFDMA is it's going to make more efficient use of the spectrum. That's the claim, isn't it? So let's look at an OFDM spectrum capture. This is a 20 megahertz channel, and we can see just 2 clients using the spectrum. But when I think about how much of the spectrum is being used, there's a big gap in the middle, isn't there? Not being used. So my question is that efficient? If we look at a non-OFDM transmission, now it's only one station transmitting, is that more efficient use of the spectrum? Now I'm only proposing the questions here. But is it more efficient to use all the channel than a little bit over here and a little bit over here with a gap in the middle? It's a question. So these were questions in my head, and I felt I really want to do some testing. Now, I know a lot of people who have done testing of OFDMA and with different results. And I'm absolutely convinced that in a lab-based environment, if you get your clients in the right location and you push just UDP traffic with, IPAD, giving it the right mix, and maybe I've heard people saying, well, what you want to do is you want to disable MCX11 because then it's going to be more reliable. You can get a really efficient OFDMA transmission. What I'm interested in is in real-world environment, is it going to be more efficient? That's the question I was trying to answer with my testing. Now, I have 6 laptops that can, with 802.11ax cards in them. So they're all Dell XPS laptops. They have the Intel AX200 chipset in. And this was the testing I did. The first test I wanted to do was just connect a single laptop up to a AP. So one AX client, only thing associated, and do a throughput test. But just TCP throughput. I wasn't trying to put any special mix. I wanted to do a very simple, normal sort of data usage test. And then the next thing I did was taking the same client is I just disabled AX and did an AC test with it. Same test, same client, same AP. The only thing I changed was I disabled AX on the client. And what was nice was I got more performance from the AX client than I did the AC client. Not much. You can see the figure on the screen maybe. The AX gave me 276 megabits. The AC gave me 230. Better modulation methods, pretty good. That's what I would expect. Then I decided to try 3 clients because the claim of AX, isn't it, is that you will only really see the benefit when we get more and more clients. That's the claim. I feel that's what we're being told anyway. By, put AX in today. You're not really going to see a benefit today, but when we've got lots of AX clients, that's when we see the benefit. So I then did 3 AX clients. And I was quite surprised and I was looking at aggregate throughput, because per client throughput, AX is never going to deliver per client. It's about the aggregate throughput. It's about what's the total available. And with 3 clients, with AX, my throughput dropped quite considerably. From the 1 client, it went to 174 megabits. I then did the same thing again. I turned all those 3 clients into AC clients, did the exact same test, and it was much better, 224 megabits per second. So it was actually a little bit more than AC on its own, but it's about the same. That was the key. It's about the same as a single client. And I did these tests vary in time, so I'm only showing you one set of results, but the results were pretty consistent. They varied a little bit, but pretty consistent. Then I said, okay, let's try 6 clients. So I did the exact same test with 6 clients. 6 clients, all AX, and my throughput went down again by about a third. Turn all those clients to AC, so now they're transmitting 1 at a time, not doing OFDMA, and my throughput went back up. If we look at this actually on a graph, I think it shows it a little bit better. So the blue is the AX, and the orange is the AC. And the first 2 graphs, that shows 1 client results. We can see that AX was a bit better. But when we went to 3 clients, the AX aggregate throughput went down quite considerably, about a third. And then we went to 6, it went down again. But the AC aggregate throughput stayed around the same level. So what do I conclude from this? Well, the first thing personally I conclude is I want to do more testing. This was one set of testing. There's a lot more I want to do. So I'm not trying to say these. I've done a few different APs, but I've not done all the APs out there. But I guess let me share with you my worry. And I think something that as an industry we've got to take seriously. We're telling people you can install AX today with today's APs, and the more AX clients you get, when you get loads and loads of AX clients, that's when you're really going to see the benefit. My worry is the opposite is true. That the more AX clients, the worse the performance is going to be, the worse the user experience is going to be. So while we've got loads of AC clients, things are going to carry on as they are today. But in the 2 years' time, when we flood these networks with AX clients, actually we're going to see a much worse user performance. That would be what my results seem to indicate. Why is that? I think there's a number of reasons. I think some of it is the overhead of the protocol. Some of it is the fact that we're not using the full channel all the time. And I think the other part of it is actually, I think maybe the scheduling algorithms in the APs need to get better. Because it's the AP that's scheduling who uses which bit of the channel when. And if that algorithm isn't efficient, then we can't expect the spectrum to be efficient. And while I was doing my testing, I found when it used uplink OFDM and when it didn't, and when it used downlink, was really random. So sometimes it would do it, sometimes it wouldn't. Sometimes you'd have one client using an RU all on its own and the rest of the spectrum wasn't being used. It seemed to be really random. And I think those algorithms have to get better. But I guess the takeaway I want to say is I think we need to think about if we're putting in the APs that exist today, what's going to be the effect when we get lots of AX clients on the network? Is it going to get better or is it going to get worse? We did some testing yesterday in the AX deep dive with John, and I wouldn't say this was really under controlled conditions because I only have 6 clients, but we did have, I think it was 16 or 18 clients all doing a test at the same time. And actually the results were similar to what I saw. The comments that people came up with straight away were, why am I getting just a few kilobits per second throughput? That's what people were seeing per station when we had 16 clients all doing OFDMA at the same time. It was down in this sort of kilobits per second throughput. So they're my results. They would be my warnings. I think we need to, as an industry, take it seriously in looking at what the actual effect is going to be when we get lots of AX clients. That is the end of my talk. Thank you very much.